All right, hello everyone. Welcome. This is the third and last of the series of 3 lectures, Aisenstadt lectures by Francis Bach. It will be another talk for specialists focusing this time on scaling laws. Will be mostly a Blackboard talk. So Francis, take it away.
Thank you, Simone. So thank you for all being here for the last talk. So this one will be, it could look a bit more technical than the other ones, but in fact, since we are all tired and cold, I will really look at the most basic types of scaling law. And the topic will be to go from linear algorithm, which will be the core of the lecture, to non-linear. Okay, and so this will be the topic. And this is joint work with so Frederik Kunstner. So Frederik. Good. I'm sorry if I misspelled, okay? And myself, okay? So this was just like recently submitted, and so all of the references are on the archive paper. So I will mention a few references, but since a Blackboard talk, I don't want to spend like the full hour like writing down the 25 references. So I will. You can check in the paper. Okay, so the topic will be like scaling laws. Okay, so what are those? Okay, so first, the name is new, but the concept is old. Okay, it's, to me, it's a rebranding of what many of us have been doing in optimization. You take the algorithm, okay, and whether you call time k or time t, you look at the performance as t grows. Okay, if you're from statistics, what grows is a number of observations. Okay, and as n goes to infinity, you have some analysis of the performance that goes down to 0. Similarly, if you do SGD, okay, you're in between stats and optimization, but similarly, you get some scaling laws. So what has changed a bit in the last like few years is that people from like neural network community have also looked at it from a totally different angle. And I should mention, so the empirical scaling laws, and the classical references, I think it's Kaplan et al., probably 2020, and Hoffman, and sorry if I misspell Hoffman, et al., 2022. And the idea here is that they do things which are a bit similar, okay? So they want to characterize the performance of their architecture with a given algorithm. But here what they introduce is a whole picture with number of observations, number of neurons, compute time, and probably also other things, batch size, and so on. So at the end, the goal is I want to have a clear picture of the performance, okay? While I run the algorithm, there's the idea being that in the middle, can I predict if I really need to spend like $200 million on more compute, okay? And so this is what they obtain. And what I like a lot, and also which I dislike a lot, is the fact that it's only empirical, okay? They posit some like polynomial dependence on the parameters, fit the data, and this is scaling law, okay? And so the goal for us will be to have some empirical evidence, theoretical evidence on the similar things. Okay, so you may wonder why it is not all done. Okay, so after like 40 years, well, even more of optimization and statistics, why can't we simply take like off-the-shelf bounds to answer those questions? There are 2 reasons. First, practice is too complex, okay? So practice okay, in the sense that, so those scaling laws done by Kaplan and colleagues, this is like for, I'm not sure, it's a bit, except for Adam on a big architecture for which we don't know to prove anything concrete, okay? And so our bounds do not apply to those cases, okay? First reason. So what I'm going to do, I'm going to simplify the problem a lot, because I don't know anybody will be able to provide any strong theoretical evidence for those type of problems, which are too complicated. Second, it's the first problem. Second problem is what we do is bounds, okay? And so having spent like many years proving bounds, I will not tell you it's a bad idea, okay? And many of us have done that in the room. And bounds have a lot of uses, because they can be used a priori. I know in advance I'm going to spend that much time to get that performance. So I think it's great. But by definition, they are bounds, okay? So they have to be pessimistic. If they're correct, they are pessimistic, okay? So what we will do today is replace bounds by limits, okay? By asymptotic equivalence. Right? So this is like a bit of a deviation from the current practice of optimization, but it brings you like really those scaling laws, okay? Of course, when you use bounds, typically you're able to focus only on the few hyperparameters. My function is L smooth and neutrally convex. That's enough to derive a bound, okay? To derive equivalence, you have to make much more assumptions, many more assumptions, okay? You have, as I will show in a moment, I will go quadratic. I will impose like eigenvalues on my Hessian. I will impose like the deviation to optimum to be a very specific form. To get this, you're not able to do this with the level of generality as you can do this, okay? So this is like the negative part. The positive part, which I find very enjoyable, is that once you have this equivalence, okay, you simply run the algorithm, you plot, it matches, and you're happy, okay? And I will present such happy plots, okay, from my own work, but clearly this is true for all equivalence. Of course, there is like the classical issue is it's asymptotic, okay? And very much like in a random matrix theory, where you get like equivalence of the eigenvalues of a random matrix when both dimensions go to infinity. When do you reach this asymptotic regime? Sometimes quickly, sometimes not quickly. And in fact, today I will have the two examples, where one, I'm going to approach it like in a polynomial like a type of decay, and sometimes logarithmic. Okay, so this has to be taken with caution. Okay, if you attain your equivalent in a logarithmic time, it's true, but it may not be visible. Okay. All right, and so the key here is that for the bounds, again, you can derive bounds where you know all the parameters. Okay, because you can often measure them. Whereas for the asymptotic equivalent, they are based on quantities which we don't know. Okay, so the practical value have to be mitigated, but this is what we're going to do. All right, so what we're going to do today, there will be 3 parts. Okay, so the first part will be the linear case. I will call it simple. Okay, essentially, what has been around for quite a few years. Okay, so essentially, what will be simple, because my Hessian will have a finite trace, and that will make the limit quite easy. Because here, what I haven't mentioned again yet is that we're going to do asymptotics in the two values in time. Okay, because we want to see what's happening when the iteration number is growing, but also in dimension. So we have 2 parameters, d and k, I will use. And so you have to be careful in the just asymptotics. And in the simple case, you can first send dimension to infinity and then focus only on k. This will be the first case. Okay, this essentially I have a blog post on it. So blog post from last year. Okay, I'm going to just go over the blog post it's like a simple math and a nice use of the Laplace method. And then second, same thing, but harder. Okay, let's not call it harder case, but essentially the limit that you're going to take between d, dimension, and time will not be like as easy. You have to couple the two the two, very much like in random matrix theory, where dimensions tend to be coupled when they go to infinity. Okay, so this is what I will do first. And I forgot to say this, the first case will correspond to essentially, if you care about machine learning, this will correspond to mostly random features, okay, random nonlinear features, okay, and what we will end up there, we will end up with a performance epsilon. So throughout my talk, I will denote epsilon the performance. I'm going to define it in a moment. And at the end, the performance will be a constant over k to a certain power. Okay, k will always be my iteration number. And in those simple cases, you get power laws on the performance. Okay, so this is very classical if you do statistics. Okay, so for the statistician among the audience, I know at least one. This is classical in non-parametric statistics. Okay, you get people fight about the correct power of k. It's not as common in optimization. Okay, but this we will do this. All right, so this will apply essentially to, if you wish, kernel methods or linear method. Okay, so any predictor which is linear in the parameters will typically satisfy such assumption. The harder case will be a good complement to the nice talk by Tony yesterday, where he mentioned that, okay, you do the muon or psion or lion, whatever, in the middle. And what do you do for the input and output layers? Okay. And what he mentioned in that for text, maybe sign descent is a good thing. Okay. And the topic of the joint work with Frederik Kunstner here is really to study that case for text. Okay, and essentially, what we will have to show is we will highlight the fact that for text data, okay, the trace of the Hessian will not be summable, and you have to use you have to consider this harder case where epsilon now will be more of the form 1 minus log k over log d. Okay, so this will be the performance. So it is decreasing in k, but much slower. Okay, the idea, and this is for gradient descent. Okay, and the idea is to highlight a fact that has been seen is that gradient descent for text problem is very slow. Okay, and what will be the third part of the talk is there have been some correcting factors. Okay, so one of them is Adam, and the other is sign descent. Okay, so I will try to argue that sign descent is a way to correct this habitual behavior, and what we will obtain is epsilon being d square over k, d over k square, d over root epsilon. No, the opposite. D over k square. So we recover power law, okay, and as I will explain later, this is an improvement on that. Okay, it's not obvious like this, but it converges quicker, highlighting the fact that for a very particular problem, sign descent has a provably better behavior than gradient descent, and the probably here is important. Okay, so it comes under many assumptions, which I will describe, but because I have limits and not bounds, that statement is formally correct. Okay, if you compare bounds, which we all have done once in our lives, okay, we should be ashamed of it, and I'm doing this all the time. You cannot claim superiority unless you have upper and lower bounds. Okay, if you have a minimax bound, sure, you can argue that one algorithm is better than the other, but to really have a formal statement, asymptotics bring you this, of course, under all the assumptions that you have made, okay, about the model and the algorithm. Okay, so I will do this one and this one in details because it seems like reasonably easy. This one I will just show the results, okay, because probably I and you will be out of steam by then. Any questions to start? Yep.
Yeah, so it's going to be distribution free, right?
Oh no. No, because no. I
There you have to solve.
no. It will be like, I think you cannot get like equivalence without making big assumptions. Take, maybe people are more familiar with random matrix theory. Okay, so for example, you take a matrix X, which is like R of n times D. Okay, and you let n go to infinity. And if you take X Gaussian, you get results. Okay, very specific. You can relax Gaussianity by being ID with a good set of moments, but it's still ID. Okay, here I'm going to go much deeper. No, deeper. Yeah, depending on what. Going to be more than this. Okay. All right. So again, if you want references for today, there's a paper by Frederik Kunstner and my blog post. Okay. All right. So let's start. All right, so let's look at. All right, so the first simplification, I'm going to optimize quadratic functions. Okay. Okay, so clearly we are not like in the transformer, whatever. Okay, so we're going to have f of x. And because I'm a nice person towards optimizers, I'm going to use the optimization notations. Okay. So not x in Rn, this is out of the question, but x in Rd. But f of x will be your parameter, and you get if you get a quadratic function, x transpose x plus b transpose x. Okay. And we're going to assume that A is a PSD. Okay, with eigenvalues. I will denote eigenvalues lambda 1 up to lambda d. Okay, you are in dimension d. And here they are non-negative. And we are not going to assume any lower bound of eigenvalues. Okay, and as d will grow, lambda d will tend to 0. Okay, so there will not be any form of strong convexity. Then I can read, once I have such a quadratic form, when A is PSD, I can write it in reduced form, where I get 1/2 of the distance to optimum. So x star will be one of the optimizers. Okay, plus f of x star. Okay, so you can always write it this way, and this is our function. Okay, so it was defined by A and B, but for the analysis, it is defined by two quantities, which is A there and x star over there. All right, so let's look at gradient descent. What is GD? Okay, so GD, it's xk being xk minus 1 minus some step size times f prime of xk. And if I write it down using that formula, I get xk minus a minus 1 minus x star. Okay, this is going to happen several times. Okay, so this is the equation. So what you obtain is that the deviation to optimum xk minus x star is identity minus gamma a of xk minus 1 minus x star. Okay, and once you have that, then you get, like, if you unroll the recursion, you get identity minus gamma a power k of x0 minus x star. Right. So this is a classical, like, undergraduate version of gradient descent. And so here you see appearing really the two quantities that are going to be very important: the A over there and the deviation to optimum at the initializer. Wow, this is correct. All right. So now that we have something like that, what you can get is a performance. Okay. So the performance will be so the deviation to optimum in function values. So f of xk minus f of x star, and because of that equation, it's just the quadratic form. So if I'm replacing this with xk, what I get is 1/2 of x0 minus x star transpose a 1 minus gamma a power 2k of x0 minus x star. Okay. All right, so eigenvalues now. Yes, eigenvalues now. Okay, so now I'm going to use the fact that A has some eigenvalues and some eigenvectors. Let's call that UI. Okay. So I can write it using eigenvalues and eigenvector. I'm going to call this A of k. And you get, so 1/2 of the sum from I equals 1 to d over the eigensubspaces. And you get lambda I 1 minus gamma lambda I times 2k times the projection of the deviation to optimum on the subspace UI square. Okay, so it's a traditional bound. All right, so now let's do first like the classic, like the bound, okay, just to highlight why the bound will be problematic. So to derive a bound for this, so I'm going to simplify my life to take gamma being 1 over L, where L is the max over the lambda i's. Okay. All right, and now to do this, okay, we're going to, we only know that the eigenvalues are between 0 and L. The traditional way is to use lambda 1 minus gamma lambda power 2k is less. So 1 minus gamma lambda is always non-negative because I've assumed gamma is 1 over the largest. I compare to an exponential minus 2k gamma lambda. Then I introduce 2k gamma and I divide by 2k gamma. Okay, and what I see appearing here is a number times exponential of minus that number. Okay, we know that because if you have v, this is v exponential minus v, you get something like this. This is minimized at 1, and the value is 1 over e. So this means that this is less than essentially 1 over 2e k gamma. And now I have the bound. And now I have the bound. So ak is less than, so all of those are bounded by a constant. Okay, so I get 1 over 4e k gamma. Okay, and all of those can be put back together. Okay, and you get the classical x0 minus x star in squared L2 now. Right, so this is a traditional. Why? Because I don't want to assume that lambda is lower bounded. This is not incorrect. Not incorrect, but if what I could have done, okay, what you mentioned is, oh, let's do this is lambda 1 minus gamma mu. Okay, and then get the exponential thing here. But this will only be interesting if lambda is not too small. Okay, and or when gamma lambda times k is not too small. And since I'm going to assume that d goes to infinity and lambda d goes to 0, I won't be able to do it. Okay, I will show examples. I will show plots in a moment. Okay. All right, so this is a traditional 1 over k bound, okay, done for quadratic functions, much easier than the convex proof. This is true for convex function up to a different factor. And this is true, but this has problems. Okay, if you look carefully here, this is the beauty of doing like quadratics, is it's all inequality, okay, everywhere, except, okay, there, but there I think it's minor, but except there, okay? What I've done here is I've taken that function v expression minus v, and I've bounded it by its maximum, okay, which is correct, but it's only tight if the argument is close to 1. What is the argument? The argument is this. So as soon as gamma lambda is close to 1 over k, it's tight. But as soon as it is far from 1 over k, it won't be tight. Okay, so this is one of the reasons why this is a crude upper bound. Okay, so what we do now is essentially do the exact same thing, but not rely on that. Okay. Any questions? Yeah.
What's going on when lambda 1 is 0? Because this estimate is still valid. The only thing that I think you need to assume is S being in the range of A.
Yeah.
And it should work. Or is there something else?
No, okay. So if, let's say I'm ordering the lambda, you mean the largest eigenvalue?
No, the smallest.
Ah, no. Okay, so here I've put things under the carpet. Okay, so here, essentially all the zero eigenvalue, you can simply discard them. Okay, and you can assume they're all strictly positive, but they can be arbitrarily small. In fact, if you take some data, any like high-dimensional data, and you A is the covariance matrix of your features, if you don't regularize, compute the lambda mean, and it's often 0 or 10 to the minus 12. Okay, and so it's very small. Often you add some regularizer to make it strictly positive, but the data itself typically is not strongly convex. All right, so before of something which I will not talk about is this is 1 over k. We could do acceleration. Okay, so in the blog post, I also do acceleration. It is simply like more complicated. Okay, so I won't do it on the board, and you get the classical 1 over k square. All right. Now the question is, how do you improve on this? Hopla. All right, so we're going to make some assumptions now. Okay, so again, if you remember on my setup, I have two quantities. Okay, I have those eigenvalues. Okay, so I'm going to make assumption. Okay, lambda I will be equal to L over I over alpha. Okay, so now this is where my big assumption comes in. Okay, I will assume this, and I will assume that x0 minus x star projected on the I'm already like in the Hilbert space, so let me go back. So yeah. All right, so x0 minus x star transpose ui. Okay, we're going to assume it's equal to delta over I to a power beta over 2. Okay, so here, those are master assumptions, okay, big ones. Okay, and I'm going to assume more things. I'm going to assume here, to make my life easier, that alpha is bigger than 1, such that the trace of A, okay, will converge to, will be convergent, finite. When D goes to infinity. Okay, so here the idea we have to let D go to infinity. So if I sum the lambda I from 1, I equals 1 to D, and the power alpha is less than 1, then I get a diverging sequence. Okay, and that would like essentially not allow me to do things with D being infinite. Same thing here. I'm going to assume that beta over 2, we're going to assume that beta plus alpha is bigger than 1, which implies that the f of x0 minus f of x star converge to a finite value. So why do you need alpha plus beta? Because if I take that quantity, this is multiplying this by the square of that, and you get 1 over I power alpha plus beta. And if you want this to be summable, you need alpha plus beta to be greater than 1. Okay, those are the assumptions. Now, relevance. Okay, so this is where the usual like hand waving comes in. Okay, and so here, let me hand waving. Okay, so this is essentially this corresponds to if you have let's say random features, nonlinear features, okay, for example. Okay, so for example, you do like I'm going to be mixed up in my notation because yeah, so let's say you have a neural network, okay? If you have a neural network and your features, phi of the data is some activation function, which I will take a ReLU of the data transpose some random W. Okay, so this is what you will get if you do a one hidden layer neural network with random input weights. If you just learn the output weights, okay, you it's not the same. You end up with features which are going to come out linearly, which are of that form. Okay, so this is a classical instance, and if you have such features, okay, so what you can show. All right, what you can show is that I'm going to be very NYV under appropriate assumption. Essentially, this corresponds to alpha being 1 plus 1 plus 3 over dimension minus 1. And so result I have from 70. Okay, so what you can show is that if your data, let's say, are on the sphere, to simplify, uniform on the sphere, the W's are also uniform on the sphere, then when the dimension goes to infinity, okay, and the number of observations goes to infinity as well at the proper rate, then you're going to have what is often called the source condition. This is often called capacity. This is called often like capacity. Okay, so the eigenvalues of your Hessians is going down to 0 at a given height. This is also, in the context of learning, this is a covariance matrix. So this is a result of the covariance operator because I'm doing like things in infinite dimension. Right. So there are arguments to highlight to show that for reasonable problems, this is true, okay, with some alpha which is bigger than 1. Okay, so there are probably other ones. And the classical references here is Caponetto, and De Vito. Okay, from I forgot when. 7. Okay, and she also there are still references by Courtney and Elliott, okay, from 2024. Okay, so if you want to know more about the relevance of that assumption, okay, this can be formalized in those papers, also in my blog, I do it. Okay, so this is for alpha. Okay, so alpha does exist, and same thing under the same assumption. Then you can have beta. So it's called the source condition. This one. The source is true as well, with beta being which may be equal to alpha if you're well specified. Beta can be equal to 0. Beta can even be negative in some cases. Okay, so this is like a reasonable assumption if you have a random nonlinear features and you're in a high dimension. Okay, so I won't say much. Yep. Well, yep.
Beta always have to be bigger than 1. So the sum of the norm is 0.
Very good point. No, I'll come back to that. I'll come back to that later.
Alpha is bigger than 1, then automatically beta plus alpha is bigger than 1 unless beta is negative, right?
Yeah, so beta can be negative. Beta can...
Right, so this is what's bothering me. So U is an eigenvector.
Yeah.
It's a scaled eigenvector. How can it possibly be growing? This is a fixed vector times.
No, no. This is no.
So U is an eigenvector, right?
Yeah. So yeah. So you can.
Is it normalized?
It is normalized. but you multiply by an arbitrary vector, and you can choose that to be as bad as you want.
But it's still-
Yeah.
Oh, because there's, okay, the dimension, right? So that can be bigger. Okay.
So there's no A here, okay? Okay. So clearly, indeed, if you want this to be non-vacuous, it's for beta negative. And indeed, if you assume that it is random feature model, that your data are misspecified, okay? So your data are not as smooth as your function, which you want to estimate is not as smooth as your model, then beta will be negative, okay? So this is a situation where indeed, and if beta is negative, okay, this will be infinite, okay? Okay, sure, but that's I'll come back to that in a moment, okay? Any further questions on the assumptions? Okay. All right, so the data assumptions. All right. Okay, so now I have assumptions, I have a formula, and now I can compute. All right, so I can compute, okay. All right, so now if I replace I use these on this expression, I get 1/2 sum from I equals 1 to D of, so I will get L delta square over I alpha coming from there and there, plus beta times 1 minus 1 over I alpha power 2k if gamma L is 1. Okay, so I'm going to use L. L is the usual L from optimization. L is my largest eigenvalue. Okay, so L is the smoothest parameter, and choose gamma being 1 over L. So gamma lambda becomes this, power 2k. And then I'm assembling lambda I and this one, okay, square. I get lambda I plus this one square, and I get back this. Okay, so this is, let me check. Yep. Okay, so this is the what we need to analyze, and because I've made those assumptions, particularly this one, okay, I can take the sum to infinity, and which I'm going to do now. Okay, so in this joint asymptotics between t, d, and k, I'm putting d to infinity, and then I just have k. Okay, this is classical in that setup. And now, once I have that, okay, to simplify things even more, and this is legit, so you can look my blog post if you want to get a justification, very informal. I'm going to replace this by an integral. Okay, so I have a series. Okay, I have a series. So I'm going to replace this by 1/2 integral from 1 to infinity of L delta square over not u, let's call it v, power alpha plus beta, 1 minus 1 over v alpha power 2k dv. Okay, so this is a classical like series to integral approximation. Okay, so this is legit. Okay, you can check that. In fact, it's not legit for the early i's, but since most of the sum will be like taken over by the let I being large, this ends up being equal to that. Okay, equivalent to that. All right. So the reason for doing so is to have to do a change of variable for simplicity. So let's do a change of variable, and I will take v. It's not like in my notes, but I can recover u being 1 over v alpha. Okay, so here I have to do a change of variable on the board. So I'm going to make mistakes. Okay, and so let's do it. Okay, so v is 1 over u power 1 minus over alpha. All right, and what I get that AK should be equivalent to 1/2 L delta square. This will not change. Okay, then I get from dv over v alpha plus beta. I should get some terms. So the integral goes from now 0 to infinity. Okay, this is fine. The 1 minus u power 2k. This is the obvious part because this is that term. Okay, and now I have to take those two. Okay, and those two, believe me, it should be du over du times u power beta minus 1 over alpha plus 1 over 2 alpha. Okay. Trust me. No, there's no plus 1. Okay. Yeah. Okay. It's really like a general variable. Okay. There's nothing, nothing major. And now, what do we have? Let's put 2 alpha. Okay. We're not physicists, so du at the end. And there is alpha over there. All right. So now, what we need to do is to find the asymptotic equivalent of such an integral. Okay, and this is where like classical results from applied math will be necessary. Why? Because you can write this as exponential of 2k of log of 1 minus u. And what you have is the exponential of something that goes to infinity times the function. Okay, and that function is maximized at 0. Okay, and we know that in such situation you can replace this integral. So this is Laplace. This is Laplace method. Okay, so you can replace essentially this, it's 0, 1, this integral by the logarithmic term replaced by its first order expansion around the global optimum, okay, and the integral being taken from 0 to infinity. Okay, so here, if you don't know Laplace, I have a blog post as well from a few years ago, and you get L over delta square over 2 times integral from 0 to infinity of exponential minus 2u times k, because log of 1 minus u around the maxima, which is maximizer, which is 0, is minus u times u power beta minus 1 over alpha du. All right, so now this is the equivalent. Okay, and here this is when k goes to infinity. Okay, so we are almost there. And now here you recognize a gamma function. Okay, so yet with another change of variable, okay, which I will not do. Okay, it's a bit easier. Okay, it's just a change of scaling. Okay, so this, trust me, this is equal to, okay, L delta square over 2 alpha, there was alpha there, times gamma of omega over k power omega, with, this is a key, omega being beta minus 1 over alpha plus 1. Yep. Okay, so this is the resulting scaling law as promised. Okay, so what has been the path to achieve it?
Is H 1 over K?
It's K.
K.
This is, yeah, this, no. Yeah, and also for the North American, this is 1. Okay. And yeah, so how has this been achieved? By making strong assumptions, okay, quadratic function, strong assumptions, and then just like doing like undergraduate calculus directly, and its all equalities, and then asymptotic equivalence. Okay, here there is no like big O. Okay, so now let's analyze the outcome. Okay, so let's analyze the outcome. First, this is non-vacuous, is omega is strictly positive, okay, otherwise kind of weird. And you can say that omega being strictly positive corresponds to exactly that, okay? So the assumption which I have made was ensuring that the thing was going down as k goes to infinity. So if you take now beta bigger than 1, okay, if beta is bigger than 1, then if beta is bigger than 1, then the norm, the square norm x0 minus x star is finite. Okay, then you can apply the convex bound, okay, 1 over k. But if beta is bigger than 1, omega is bigger than 1. Okay, so this is like not totally like insane. Okay, so if you can apply the convex bound, the equivalent is better than the convex bound. It has to be, because one is a bound and one is an equivalent. Okay, you recover this. But what you recover as well is omega is better than 1. Okay, it does convert faster. Okay, for that model. Okay, so this is one of the reasons why I will show plots where things differ. All right, so one extension which is in the blog post is if you don't like this assumption, okay, and you want this to be true on average, like the expectation of the square of this is the square of that, it's okay. Okay, so if this is only a random model, it's also fine. Okay. And now let's look at some plots. And I will take questions. Now I will see if the technology is working. Oh. All right. Yeah, it's not big. Okay, so this is okay. So this is like, so here I'm plotting okay. I'm plotting several curves. Ooh la la, very good.
Miracles of technology. This is a real TV station.
Indeed. All right, so here, so don't look at this. Yeah. But now it's supposed to be for the lower plot. Okay, so here this is the performance in black. Okay, this is a black line. The estimate asymptotic is following the black line. Okay, so here you see like some going down because I haven't taken d big infinite. Okay, so as is always the case, if you don't take d big infinite, at one point you get to see the linear convergence. Okay, so here d is not too large because I have a small computer. Not even this is because in the blog post I'm taking this from. I do the full strongly convex case. Okay, so let's forget about that part. So it follows. Okay, so it's not always touching, but it's touching when k is big enough. In red, this is non-strongly convex bound 1 over k. Okay, it is correct. Okay, but it's above. And in blue, this is a strongly convex bound. Okay, which I was mentioning earlier. Since lambda mean is very small, it's non-zero, it's very small, it's flat, and then it starts to optimize. Okay, this is a really classical example. And then sometimes this is a funny part. Okay, so this is if my omega here is less than 1. Okay, so omega less than 1 means that beta is less than 1. So the convex bound must have a problem. Okay, so here this is the convex bound, which is still not infinite because d here is not infinite. I took d being, I forgot, but it starts very high. Logarithmic, okay, I forgot to mention this is like semi-log, this is log. Okay, so a line is a power, okay, and so the non-convex bound starts to be like very large because the distance to optimum in square norm is like very large, so it's very bad, but it gets at the end reasonable. And yeah. All right. So this is for the easy case. Any questions on those bounds? So if you want, there are more things. Okay, now I can stop. Okay, so a few extensions of those, like of that bound. Okay, so you can do acceleration, okay, where you will get essentially a power of omega plus 1 or 2 omega. You can do SGD as well, and this has been done by Courtney, Elliott Paquette, and other people. Okay. Yeah, so you can extend, okay, but I will not go that way. Any questions? No? All right. So now let's tackle the harder case. Okay, the harder case will be. So we simplify the harder case. So we use the same thing. Okay, I will use the same thing. I will use assumption that lambda I is 1 over L over I. Okay. Okay, and I will use this being delta. Okay, essentially. Okay, so there is no more. So trace A is infinite. Trace of A is infinite. If D is infinite, and this is infinite as well. Okay. Okay, so we see that we start to have some problem. So what is the relevance for this? Okay. Okay, so what is the relevance is essentially the Bigram model. So Bigram. So what is the Bigram model? The Bigram model is, so you have there's some text. It's like let me check something. Yeah. So what is the Bigram model? So you want to predict the next word. Okay, it's next token prediction. Okay. So this is like the super dumbed down version of GPT. Okay, so you observe some text, and you want for every token, okay, predict the next one. Okay, clearly transformers predict from the whole past. Okay, so we're just doing the next token prediction. It's called a Bigram model, and this is like NLP from 20 years ago. Okay, and so yes, so and then the way you do it, you have token X, and you want to predict. So yeah, I'm going back to machine learning assumptions, notation, otherwise we get totally lost. Okay, so you have a token X, you want to predict the next token Y. Okay, and the way we're going to do it, the token X will be with a one hot using one hot encoding, so 0, 1 to the power P. If you have P, a vocabulary of P tokens, and Y would be also in 0, 1 to the P. Okay, so what you have here is a prediction from P dimension to P dimensions. Okay, and the way we're going to model it is using a linear model. Y will be essentially W times X. Okay, but W is of size P times P. Okay. Right, and so this is the model. I'm going to use square loss. Okay, I'm going to use square loss, which is for every observation y minus wx square in the L2 norm. And now I'm going, if you take some data, you're going to sum this over your data. Okay. And so what I'm claiming, and I won't have time to give you the full proof of that because it take me like 10 minutes, is that with that problem, okay, we can compute the Hessian. Okay, so here it's a bit more complex because it's a problem in size p square. Okay, it's a pretty big problem because number of tokens can be like 10 to the 8. Okay, so don't run this on your computer. And you can compute the eigenvalues because I have one hot encodings like this. Then when I take the rank 1 matrix for the second moment, it's going to be diagonal because it's one hot encoding, and so the Hessian for that problem should be diagonal. Okay, so what you can get is that A will be diagonal, and what it will be composed with word frequencies. Okay, so for for every token, you can compute its frequency in your data set, and A will be diagonal with the token frequencies. Okay, those are the token frequencies. Okay, then you know what is A. You can compute the optimal W star. Okay, this is a Bigram model. This is closed form. Okay, this is essentially the for every input token, it's going to be the probability of the output token. Okay, so you know can compute W star. Okay, and then if you know W star, you know the deviation between x0 and W0 and W star. Okay, since the A is diagonal, the eigenvectors are just like a canonical basis. So you just need to look at the components of, if you start from 0, of W star. Okay, and the assumption that we have here is to say that the eigenvalues, which are the token frequencies, are of the form 1 over I. Okay, so this is what is wasn't in abstract. It's a zip flow. If you order the token by frequency of appearance, they decay as 1 over I. I will show a plot. Okay, and now for this assumption, okay, it is not true that next word prediction is constant, but because we have square loss, okay, each output token will be predicted separately because you have square loss. Okay, the class we do square loss for multi-class, you get separation of all classes, and you begin to sum over all tokens. Okay, and if you just use the assumption that for each token, given token, the next token has also a zip flow, but with different ordering than the data. Then if you sum over tokens, you get a constant. So I will not give you details. I will just give you the fact, how true is this in the data? How true is this in the data? So let's look at technology again. Lance la diffusion. Yes. Technology cannot. No technology. Then you have to believe me. No, it's there. All right, so this is like the word frequency, okay, done on some data which I have no clue, but it's on the paper. And you see the rank of the word k, and you see the frequency. If you fit 1 over k, it's a reasonable match. Okay, so this has been observed by many people. Okay, it's not really our findings, of course. So this is for the eigenvalues of A, and this is for the conditional frequencies. Okay, so here we assume that for every token J, okay, the next token, okay, frequencies also follow the same zip flow. Okay, and this is what we plot for every word. We plot like for every word. So we have one curve per word per input we have one curve per input word, and we plot all of them. And you see that it's more or less like 1 over k. So it's more or less. Okay, so clearly here our assumption on the delta, the distance to optimum, will be quite an approximation. Okay, but just to highlight the fact that we are really in a 1 over k type of behavior and not 1 over k alpha, where alpha is bigger than 1. Right? So just to justify the assumption. Any question? Yep.
If you use diagram on more, would that also do?
Very good question. Probably, but now you have like it's not a matrix W, it's a tensor, and yeah, probably. What I don't know is whether if you condition on 2 words, do you still observe the power law? Maybe it's too reduced when you have 2 words. There are only like a few tokens. I don't know, but I think it's a good point. We haven't considered it, but that's clearly something that you could consider. Any other question? Yeah.
1 over k to the 1.2, how much changes in your plan?
What, okay, so it will change the behavior significantly. This is where asymptotics has a problem. Okay, if you do non-asymptotic and alpha goes to 1.01 to 1, you don't care. If you do asymptotics, okay, you have two different regimes, and clearly in the paper we do the three regimes, alpha bigger than 1, alpha equal to 1, alpha less than 1, and there's no continuity there. Okay, there's a discontinuity in the bounds, okay, which we try to mitigate by having like a less asymptotic bound, but it's a mess. Okay, so clearly here, if alpha is 0.99, you're in between 1 and less than 1. Okay, I don't have a better answer to this, and that's why I'm focusing on alpha equal to 1. Okay, any further question? No? All right, so let's do the math, but the math will be very simple. All right. All right. I have to unshare. All right, so the math is still there. All right, so now let's use those assumptions. It's just the same as before with alpha being 1 and beta being 0. So let's do that. So alpha is 1, beta is 0. Okay. So this is, and now, okay, now we go to sum from 1 to d. Okay, let's not do this for the moment. All right, now we want to study this. Okay. Okay, so first difficulty. Yeah. Okay. Alors, let's first like outline the difficulties. Okay. And the workarounds. So first difficulty, we're in a setup where when d even at time 0, okay, when this goes away, okay, the limit when d goes to infinity will be like of the order log d. Okay, so when I take d being infinite or tending to infinity, even my performance at initialization blows up. Okay, so first difficulty. Okay, A0 goes to infinity when d go to infinity. So the workaround is let's compute a k over A0. Okay, so we're going to only look at the relative progress. Okay, and when d goes to infinity, you start with 1 and you want to decay with 1. Okay, so first difficulty, this is reasonable. All right, second difficulty, which is more important, is so now again being over 0, this is so so the good thing, the constants go away. So you get sum over I from 1 to d of 1 over I, 1 minus 1 over I, 2k. Yeah, over log d. Okay, so here, this is a harmonic series I'm putting into log d. All right, so second difficulty is that, which is stronger. So if k is fixed, the limit when d goes to infinity will be equal to 1. Why is this the case? Because if k is fixed, okay, and you let d go to infinity, you have a sum of a diverging series, okay, and that term will start to be vanishing, equal to 1. So essentially, you get those two terms being equal. Okay, so trust me, when k is fixed, okay, and d goes to infinity, then this will make no progress. Okay, so it's a classical situation that if you don't do joint asymptotic, if you fix one of them, you get like trivial answers. Okay, so this is one difficulty. Okay, and the way, and so the workaround, okay, will be to take that k will be a function of d. Okay, so you need to let k and d go to infinity together, okay, and very much like a random matrix theory, it won't be k over d go to infinity together, but it won't be k over d constant. It will be a bit more complex. All right. So now what is a good factor? Okay. So all right. So now let's do some computations. Oops, sorry. All right. All right. So first simplification. Okay, we're going to make our life simpler. We're going to take AK over A0. We're going to replace integrals, sums by integrals. Okay, this we have been doing this already several times. So the log D is not perfect. It's correct. 1 to D of 1 over, let's call it T, 1 minus 1 over T over D, over 2K, sorry, dt. All right, not a complete integral. Let's do a very, so here I'm going to do something very arbitrary, okay? You may think it comes from nowhere, but since I'm going to end up with a non-trivial statement, it means it was the correct choice, okay? And I could like hand wave how we found it, but let's not go there. And let's do a general variable, T. Let's do T equals D power Z, okay? And why it is the case? Because if you look here, okay, so the time has to depend on D. So if the time grows bigger than D, okay, this will be 0, okay? So we know that if K is too large, bigger than D, you get a trivial result in the other direction. Everything is 0. So we go in between, okay? And the in between is not a ratio. It's not a ratio. It's a power, okay? And this will work out very well. And so if Z is this, then you get Z will be log T over log D. Log K, sorry, was T. In fact, it's more 2T. All right. So, yeah. And so if you do the change of variable, you get 1 over log D. The integral, okay, from 1 to D, and the Z should be, I'm getting tired, so I'm going to check on my notes because 0 is a bit 0 to 1, okay? Yeah, it's 0 to 1. So there may be, let's simplify my life and remove the 2, okay? And then things will be easier, okay? So there's a way to make things correct, but unless you want to spend the lunch here, it won't work, okay? And so so the good thing is that dt over t, okay? Dt over t will be exactly log d, okay? So this is the whole point, okay? So dt over t will be log d times dz, okay? So you get 1 minus d to the power minus z times t, which is d. I'm mixing everything. Oh, okay, let's. Yeah, this is really like out of steam. Yeah, so K doesn't move. It's K is fixed. Okay, no, not too bad. Okay, K is fixed. Okay, yeah, and dz. Okay, so this is just a change of variable. And now I'm going to take my fancy scaling. K will be d power tau. Yeah, K will be d power tau. And now this is like d power tau. Okay, and now the log d disappears because dt will be log d dz. Dt over t will be log d dz. So this goes away. Again, start again. This is t. So if you do the change of variable, okay, it's an exponential function with not exponential but a d. So you get a log d that will disappear with this one. Okay, and now you're in good shape because now you can. When d goes to infinity, okay, you can check that if everything will depend whether, let's write it as 1 over dz. Everything will depend whether tau is bigger than z, okay? If tau is bigger than z, this will be 0 when d goes to infinity, and if tau is less than z, that will be 1, okay, in the limit, okay? Or the other way around, but at the end, it should be equal to integral from 0 to 1 of 1 of z bigger than tau. Okay, so this is where the limit comes in, and now it's legit, quote unquote. It's not a double limit, okay? Since I've assumed k is tied to d, okay, with tau being fixed, now I have one limit, which is d goes to infinity. The limit will depend on tau, okay, but I have a single limit. If I take that single limit, okay, those two go to infinity, okay, depending which one is over the other, it's either 1 or 0, and it's 1 when z is bigger than tau, and so if you complete the integral, you get 1 minus tau. Okay, so at the end, what have we showed? We have showed that the relative decrease of gradient descent is of that form, in the asymptotic equivalent to 1 minus tau when k is of that form. Okay, so you can see this, you can put it in various forms. You can either take tau is log k over log d. Okay, so you get what I was promising, 1 minus log k over log d. You can invert it, okay? You can have k as a function of the precision. So this is like epsilon. And you can get this is equal to d power 1 minus epsilon. Okay, so if you prefer fixing the relative precision, relative error, okay, and see how much time you need to converge, this is the scaling law. Okay, so we used to have 1 over a power of epsilon for the classical case. Now it's a different. Epsilon is in the exponent, and what it shows is that if you want a good model, epsilon being small, you can go up to O of d in terms of running time. So this is what was observed by Frederik Kunstner in earlier work, is on text data, when you have more tokens, it takes even more time. Okay, so not only every iteration is slower, but you do more iterations. Okay? So it's one instance of a scaling law. Okay, and you may wonder, do we see this in practice? Okay, so let's look. And that would be almost the end. Where am I? Am I here? Partager. So this is okay. So this is a result where this is our like new notion of time. So t is k. Okay, I don't like t, but Frederick insisted on t, so I have no choice. Okay. So k is t, and this is a new tau is my tau, which is over there. And as tau is growing, this is a new notion of time. This is in color, this is like d growing, okay? And this is in color, this is the true performance, and in black, this is the asymptotic bound. Okay, so this is for data following my model. Okay, data from really like the zip flow. Okay, so this is like just checking the result. Okay, this is what I mentioned, like satisfying like plots is that you make some assumptions, you do some math, you plot, it matches, you're happy. All right. And now let's compare with real data. Okay. So now this is real data. This is a true Bigram model. Okay. So now this is you optimize. Okay, you optimize with a t. You optimize with t steps. Okay, here it's a real data with words coming from some data set. This is like t in logarithmic scale. This is the relative error. Okay, from 1 to 0. Okay, let's forget about the orange curve. So GD is in black, and our limit is in dotted. Okay, so I would say it matches reasonably well. It's not perfect match because our assumptions was quite close for the eigenvalues, not as close for the distance to optimum. Okay, so this is for gradient descent. Okay, so the scaling law, which is like of the form of that form. This is what you observe on that real problem. So here, real problems, I should put like many quotes. The Bigram model will never be solved by using optimization. Okay, the Bigram model is closed form. Okay, so don't use this to compute a Bigram model. That would be a waste of your time and of your computer. Okay, it's just a model which is a proxy to language modeling on which you can show that the scaling law has a given form. Okay, so this is like important to keep this in mind. Any questions on that plot? Yep. I wouldn't know. I'm sorry.
Say more about this. These are just text. You compute the unigram frequencies and the.
Yeah. So I have my context problem, the Bigram model. I know the solution, and I run GD. Okay, and I compare the performance of GD. This is a true plot. This is what you will get in optimization. We have seen like many of those plots this week, and this is just our approximation by using simply but no parameter, because we have assumed like everything is fixed and we have normalized everything. Okay, so here also we have removed the constants by taking relative progress. It should be 1. It's not 1, but let's say it's 1. Okay. Right. So what I will not do, okay, because I think it's I'm almost over time, is to look at this other one, sign descent. Okay, so here for sign descent, again, this is like a proxy. What is sign descent? Let me just define it and then give the bound, and I will stop there. So what is sign descent? So xk will be simply xk minus 1 minus a constant times the sign taken component-wise of xk minus 1. Okay. So it's a proxy to Adam. Why? Because Adam will rescale by previous gradient. And if you take a memory of 1, it's rescaling by yourself, so it's a sign. Okay, so it's a proxy, and we are not the first ones to look at it as a proxy to Adam. There are arguments to say this could be even better than Adam. Okay, but this is what we study. And so here it's a non-linear algorithm. Okay, why? Because f prime, since we have quadratic f, is linear in x, but the sign is non-linear. Okay, so why is this possible for us? It is possible for us because f, the Hessian is diagonal, it decouples. Okay, because we have least squares, every token decouples. So at the end, everything decouples. Okay, so we end up by doing sign descent in 1D. And if you're in 1D, what is sign descent? It's a function. So sign descent goes either left or right. Okay, so if you start on the left, you're going to make constant steps. Okay, and once you reach the global optimum, you're going to oscillate. Okay, with oscillations which are of order gamma. Okay, you will never hit the exact optimum because the step size is constant. Okay, you oscillate. And what we end up doing is analyzing this, and since everything decouples, because we have a simple model, we can get a bound. And the bound that we get is k being, what is this? K being, okay, so ak over A0 is a constant over tau square. And so I think it was d, or square root of d over epsilon, something like that. I'm not sure that the under is like inside or outside, but that's fine. All right, and so let's go back to my plot here. Yeah, so what it shows is that, okay, after some not complex math but a bit tedious, is that this is a scaling law for sign descent. This was the one for gradient descent. So if you take epsilon quite small, this is O of d. This one is O of square root of d. Okay, so it's one instance that probably under many assumptions, sign descent is better. Okay, and this is on the real data. Okay, so I have the same plots where we show that our bound matches when you have like fake data, but with real data, this is side descent in black. Okay, and so it does improve over gradient descent. Okay, after a while, and this is our asymptotic behavior in dot. Okay. All right. One other thing maybe is you may try to use the scaling law to check that to reach some precision, how much time do you need? And I'm claiming that the time grows as a power of 1 minus epsilon. Okay, and this is like not totally true, but this is like a hint that it provides some predictive power. So here again, it's very specific, very loose. And then I think, yeah, let me now conclude. All right, so what have we done? Okay, so essentially we have taken that classical, like quadratic gradient descent bound, which we often do in class, and I've made some assumptions on eigenvalues. Okay, those assumptions were always of the form, but they're gone, like 1 over certain power. Okay, and the key was to check that the power was either more or less than 1. And if you have the classical case where the power is bigger than 1, you get scaling laws in terms of k as being a constant over epsilon to a certain power. And if you use like the other regime, okay, so here I've done only alpha equals 1, but we have in the paper alpha less than 1. Then you get other type of scaling laws where epsilon is now in the exponent. Okay, they match very well for fake data by design. They match a bit for real data. All right. Then we do sign descent, which is also like a power law. Very good. Okay, so first, before I conclude, limitations. There are many limitations. Okay, so let me list them one by one. Quadratic. Okay, it's not really what people use. Linear model. Okay, we are far from neural networks. We don't accelerate. We don't do SGD. Okay, so at the moment this is reasonably simple because we have made so many assumptions. Clearly, the goal will be to remove some of them, but it's not always easy. On this, I will thank you for your attention.
Thanks a lot for the great lecture. So we do have a couple of minutes for more questions. Yes.
So if I understand correctly, the sign descent is basically doing kind of steps along towards coordinates of a cube, not coordinates, corners of a cube, right? So you...
if you wish to see it that way, but it's simply like the steps are always in -1, 1 times gamma.
Right, exactly. Yeah. So what about, just scaling the gradient, and so it will be on a ball times gamma, right?
It won't work here because it will recouple everything.
Okay, so that is essential that you have decoupling.
Yeah, because you need decoupling by token, by output token. This is due to square loss, and by input token, this is due to diagonal Hessian. If you take like the sphere, you recouple the input tokens, and then I don't know how to do it.
Okay.
It may be doable, but yeah.
Any more questions?
Thank you for the talk. In your example, you use a square loss for that classification task. Do you think your results still hold when you consider cross entropy loss for those classification tasks in the token prediction task?
It's empirically it does. Okay, so the behavior as it gets harder when D increases is still visible, but the bound is not correct for sure. Okay, because if you use cross entropy loss, okay, so the Hessian also decouples, but the cross entropy loss will couple all output tokens, and nothing is closed form. So here, why it works? Because everything is closed form. Okay, so as soon as you remove this, I don't know how to do it. Okay, so that's probably a possibility if you maybe if you go like continuous time, continuous space, but you get an ODE which is not closed form, so that's a good thing to try. But our goal was to remain as simple as possible. And yeah, good point. But I don't know. I don't think it's true, really, of that form. But there has to be a similar form. Yeah.
Any final question for the speaker? All right. So let's thank Francis again.